The Roots of AI is an engaging series that delves into the captivating history of artificial intelligence. This collective release comprehensively covers the transformative journey of AI from the 1930s to the 1940s, ultimately leading to its remarkable success in the present day. Let's get started. 1936. Turing machine. Alan Turing's work on the Turing machine, introduced in his landmark paper on computable numbers, with an application to the Entscheidungs problem in 1936, laid the foundation for the development of computers and the field of computer science. Turing's concept of the Turing machine was a theoretical model of computation that revolutionized our understanding of what can be computed and how machines can simulate human intelligence. A Turing machine consists of a finite set of states, a tape divided into squares, and a head that can read and write symbols on the tape. The machine starts in a particular state, and it reads the symbol at the current position on the tape. Based on the symbol it reads and the current state, the machine follows a rule to determine its next action. The action might be to write a new symbol on the tape, to move the head one square to the left or right, or to change to a new state. The machine continues to follow rules until it reaches a state where it halts. The Turing machine can be used to solve any problem that can be solved by a computer algorithm. The key features of Turing machines. 1. They are deterministic, meaning that they always follow the same rules in the same order. 2. They are finite state, meaning that they have a finite number of states. 3. They have unlimited memory, meaning that they can store an infinite amount of data on the tape. Turing's key insight was that any computation that can be described as a set of well-defined rules can be performed by a Turing machine. This concept led to the idea of universality, which means that a single machine could simulate any other machine given the appropriate instructions. In essence, Turing showed that a universal computing machine could be created that could imitate any process that can be described algorithmically. The Turing machine was a significant breakthrough because it challenged the prevailing view that mathematical computation was limited to what could be achieved by human mathematicians. Turing demonstrated that a machine could perform calculations and simulate any computable process, effectively blurring the distinction between human computation and machine computation. The concept of the Turing machine had profound implications for the development of AI. Turing himself recognized the potential of machines to exhibit human-like intelligence and proposed the question, can machines think? In his influential 1950 paper, Computing Machinery and Intelligence, this question became the foundation for the field of AI and sparked decades of research and exploration into creating intelligent machines. Turing's work also highlighted the importance of algorithmic thinking and formalized the notion of computation. The idea that complex problems could be broken down into a series of simple, well-defined steps that can be executed by a machine formed the basis of algorithmic problem solving, which is central to AI. Furthermore, the Turing machine has established a theoretical framework for comprehending the boundaries and potential of computation. Alan Turing demonstrated that there are specific problems, referred to as undecidable problems, which cannot be resolved by any algorithm or Turing machine. This notion of undecidability has become a fundamental concept in the field of theoretical computer science, and has played a significant role in defining the limits of computational possibility. The notion of the Turing machine influenced subsequent AI research and led to the development of symbolic AI, which aimed to create intelligent machines capable of symbol manipulation and logical reasoning. Turing's work also laid the groundwork for the development of programming languages and compilers, which transformed the way we interact with computers and made it possible to write complex software systems. In summary, Alan Turing's concept of the Turing machine was a groundbreaking contribution that revolutionized our understanding of computation, and laid the foundation for the development of computers and the field of computer science. The Turing machine demonstrated the possibility of creating a universal computing machine that could simulate any process, describable by a set of rules. This concept had a profound impact on the development of AI, shaping our understanding of computation, algorithmic problem solving, and the limits of what machines can achieve. Turing's work continues to influence and inspire advancements in AI research and computational theory to this day. (1943) McCulloch-Pitts neuron. In 1943, Warren McCulloch and Walter Pitts introduced a groundbreaking concept in the field of artificial intelligence, the McCulloch-Pitts neuron. This revolutionary idea laid the foundation for the study of neural networks and computational models that are inspired by the functioning of biological neurons. McCulloch and Pitts' work has had a profound impact on the field of AI, as it has allowed researchers to better understand the complex processes that occur within the human brain. By modeling these processes, scientists have been able to create machines that can learn, reason, and make decisions in ways that were once thought to be impossible. The McCulloch-Pitts neuron was a simplified model of how a biological neuron works. It aimed to capture the basic principles of neural activity, and develop a computational model that could mimic certain aspects of the brain's information processing capabilities. The key idea behind the McCulloch-Pitts neuron was to model the behavior of a biological neuron as a binary decision-making unit. It received inputs from other neurons, each associated with a weighted connection, and produced an output based on a specific threshold function. The neuron's inputs were binary signals, representing the activation or non-activation of other neurons. Each input was multiplied by its associated weight, and the weighted sum of inputs was passed through a threshold function. If the sum exceeded the threshold, the neuron would fire and produce an output signal, otherwise, it would remain inactive. As such, a McCulloch-Pitts neuron has three main components. 1. Inputs. The neuron can receive any number of inputs, each of which can be either 0 or 1. 2. Threshold. The neuron has a threshold value, which is a real number between 0 and 1. 3. Output. If the sum of the inputs is greater than or equal to the threshold, then the output of the neuron is 1. Otherwise, the output is 0. Based on these components, the key features of McCulloch-Pitts neurons are: 1. They are binary, meaning that they can only have two states, 0 or 1. 2. They are threshold, meaning that they only fire if the sum of their inputs is greater than or equal to a threshold value. 3. They are interconnected, meaning that they can send signals to each other. This binary threshold model of the neuron was significant, because it provided a formal framework for understanding computation in terms of simple, interconnected units. It allowed researchers to explore the behavior of interconnected neurons, and investigate how networks of such neurons could exhibit complex patterns of information processing. The McCulloch-Pitts neuron formed the foundation for subsequent research in neural networks and connectionist models of computation. It provided a starting point for developing computational models that aim to simulate and replicate certain aspects of human cognition and intelligence. The neuron's simplicity and binary nature made it amenable to mathematical analysis, allowing researchers to study its properties and explore its capabilities. McCulloch and Pitts demonstrated that their binary threshold neuron could perform logical operations, such as an operation, an OR operation, and could be interconnected to create more complex computational systems. The McCulloch-Pitts neuron also played a crucial role in the development of the perceptron, a single-layer neural network capable of learning and making decisions. The perceptron, introduced by Frank Rosenblatt in 1958, expanded upon the concepts of the McCulloch-Pitts neuron and introduced the idea of adaptive weights that could be modified during learning. Rosenblatt's perceptron extended the binary threshold model by introducing a learning algorithm that adjusted the weights based on the input data and desired outputs. This allowed the perceptron to learn from examples and make predictions or classifications based on its learned knowledge. The perceptron and its learning algorithm became an influential concept in AI research and machine learning. Although the perceptron had limitations and could only learn linearly separable patterns, it paved the way for more advanced neural network architectures and learning algorithms that emerged in later years. Overall, the McCulloch-Pitts neuron was a fundamental contribution to the field of AI. It provided a simplified computational model of a biological neuron, and offered insights into how networks of interconnected neurons could exhibit complex information processing. The concepts introduced by the McCulloch-Pitts neuron laid the foundation for subsequent research in neural networks, connectionism, and machine learning, shaping the development of AI and inspiring further advancements in understanding the computational aspects of biological systems. (1948) Cybernetics. In 1948, the renowned mathematician Norbert Wiener published a groundbreaking book titled Cybernetics, or Control and Communication in the Animal and the Machine, which introduced the concept of cybernetics. The book was a bestseller and had a major impact on the development of many fields, including computer science, artificial intelligence, and neuroscience. Wiener's work laid the foundation for the study of control and communication systems in living organisms and machines, significantly influencing the development of artificial intelligence, AI. Wiener's book was a seminal work that revolutionized the way we think about control and communication systems. His ideas were ahead of their time and have had a lasting impact on the field of AI. Wiener's work was instrumental in shaping the development of AI, and his ideas continue to influence the field to this day. Wiener's book was a tour de force that explored the complex relationship between living organisms and machines. His insights into the workings of control and communication systems have been invaluable to researchers in the field of AI. Wiener's work has helped us to better understand the nature of intelligence and has paved the way for the development of intelligent machines. The term cybernetics derives from the Greek word kybernetes, meaning steersman or governor. Wiener adopted this term to describe a unified framework for understanding and studying systems that involve communication, control, and feedback. Wiener's core idea was that systems, whether natural or artificial, could be seen as information processing and feedback control systems. He emphasized the importance of feedback mechanisms, which enable a system to receive information about its own state and adjust its behavior accordingly. One of the key insights of cybernetics was the concept of negative feedback. Negative feedback is a control mechanism in which a system uses information about its output to make adjustments that counteract any deviation from a desired state. This mechanism allows systems to self-regulate, maintaining stability and achieving goals. For example, a thermostat uses feedback to maintain a constant temperature in a room, The thermostat measures the temperature of the room and compares it to the desired temperature. If the room is too hot, the thermostat turns on the air conditioner. If the room is too cold, the thermostat turns on the heater. Wiener applied cybernetic principles to a wide range of fields, including biology, engineering, communication theory, and even social sciences. His work emphasized the similarities between natural and artificial systems, blurring the distinction between living organisms and machines. The concept of cybernetics was significant for the development of AI in several ways. 1. Understanding feedback and control. Wiener's focus on feedback mechanisms and control systems provided AI researchers with a powerful framework for understanding how intelligent systems can adapt and self-regulate. Feedback loops became central to the design of intelligent systems, allowing them to learn from their environment and adjust their behavior accordingly. 2. Information processing. Wiener's emphasis on information processing in both living organisms and machines highlighted the importance of encoding, decoding, and transmitting information. This concept influenced the development of AI algorithms that process and manipulate information to solve problems and make decisions. 3. Biological inspiration. Cybernetics drew inspiration from the functioning of the nervous system and other biological processes. This biological perspective influenced AI research, particularly in the field of neural networks, where the structure and functioning of artificial networks were designed to resemble biological neural systems. 4. Interdisciplinary approach. Wiener's interdisciplinary approach, encompassing mathematics, engineering, biology, and other fields, encouraged collaboration and cross-pollination of ideas. This interdisciplinary nature of cybernetics laid the groundwork for AI research to draw insights and methodologies from various disciplines, fostering a multidisciplinary approach to solving complex problems. 5. Ethical and social implications. Wiener also recognized the ethical and social implications of cybernetics and AI. He raised concerns about the potential impact of intelligent machines on society and advocated for responsible and ethical development and use of technology. Overall, Norbert Wiener's concept of cybernetics provided a unifying framework for understanding systems that involve communication, control, and feedback. His work significantly influenced the development of AI by emphasizing the importance of feedback mechanisms, information processing, and the similarities between natural and artificial systems. The principles of cybernetics continue to shape AI research, particularly in areas such as adaptive systems, machine learning, and robotics, as well as fostering a holistic and interdisciplinary approach to AI development and its societal implications. (1948) Information theory. Claude Shannon's groundbreaking work on information theory, published in his paper, A Mathematical Theory of Communication, in 1948, revolutionized the understanding and quantification of information. Shannon's theory laid the foundation for the field of information theory and had a significant impact on the development of artificial intelligence. In his paper, Shannon introduced the concept of information entropy as a measure of uncertainty in information content. He defined entropy as the average amount of information required to encode a message, considering the probabilities of different symbols occurring. Shannon demonstrated that entropy provides a fundamental limit on the compression and transmission of information. The concept of entropy in information theory is similar to entropy in thermodynamics, which measures the disorder or randomness of a physical system. However, in information theory, entropy is used to measure the uncertainty or randomness of a message, irrespective of its physical form. Shannon's entropy approach is used in many fields such as cryptography, language modeling, data compression, and computer security. Entropy, as estimated by Shannon theory, is a measure of the uncertainty regarding which outcome will be achieved from a set of possible outcomes. When outcomes are highly unpredictable, the entropy is high. On the other hand, when the outcomes are highly predictable, the entropy is low. Shannon entropy is calculated as the logarithm of the reciprocal of the probability of an event. In simpler terms, Shannon entropy measures the amount of randomness in an event's probability distribution. In information theory, entropy is also related to the amount of information that can be transmitted over a communication channel. The entropy of a message is the maximum amount of information that can be transmitted over a channel with perfect transmission, and no noise. This means that any message with entropy greater than the capacity of the channel cannot be transmitted perfectly. The capacity of the channel is determined by its bandwidth, signal strength, and noise level. The significance of Shannon's work on information theory in the development of AI is multifold. 1. Data compression. Shannon's theory provided a mathematical framework for data compression, which is a fundamental aspect of AI. His insights into entropy and information content laid the groundwork for developing efficient algorithms to compress data and store, or transmit it more effectively. Data compression techniques have become vital in various AI applications, such as image and video compression, natural language processing, and storage efficiency. 2. Communication and data transmission. Shannon's work had a profound impact on the understanding of communication systems and data transmission. His theory allowed researchers to quantify the capacity of communication channels and determine the optimal encoding and decoding strategies to maximize the transmission of information while minimizing errors. These principles influenced the development of efficient communication protocols, including those used in AI systems for exchanging information and data. 3. Decision theory and Bayesian inference. Shannon's theory of information provided a theoretical basis for decision theory and Bayesian inference in AI. His concepts of entropy and information content align with the principles of decision-making under uncertainty and probabilistic reasoning. Shannon's work influenced the development of AI algorithms that make decisions based on uncertain or incomplete information, including Bayesian networks and probabilistic graphical models. 4. Algorithmic complexity. Shannon's work on information theory contributed to the understanding of algorithmic complexity and the limits of computation. His concept of entropy can be related to the complexity of a message or a data set. This notion has implications for AI, as it helps researchers understand the inherent complexity of problems and the computational resources required to solve them. 5. Machine learning and pattern recognition. Shannon's work provided insights into the representation and extraction of patterns in data, which are crucial aspects of machine learning and pattern recognition. His theory of information content and entropy influenced the development of algorithms for feature selection, dimensionality reduction, and statistical modeling. These techniques are fundamental in AI systems that learn from data and recognize patterns to make predictions or perform tasks. 6. Artificial neural networks. Shannon's work influenced the development of artificial neural networks, a key component of AI. The principles of information theory, such as entropy and information content, have been integrated into the training and learning algorithms of artificial neural networks. Shannon's insights into information processing and communication provided a theoretical foundation for understanding how artificial neural networks can learn and encode information. 7. Practical applications. Shannon's work on information theory has found practical applications in various AI domains. It has influenced the development of speech recognition systems, image and video processing algorithms, natural language understanding, data mining, and recommender systems. The principles and techniques derived from Shannon's theory are used to optimize data representation, encoding, and transmission in AI applications. Claude Shannon's work on information theory fundamentally transformed our understanding of information, communication, and computation. His concepts and principles continue to shape AI research and have practical applications in various domains. Shannon's theory provided the mathematical foundations for data compression, communication systems, decision theory, and machine learning. The integration of information theory in AI has enabled the development of more efficient algorithms, improved data processing techniques, and advancements in pattern recognition and probabilistic reasoning. Shannon's contributions remain pivotal in the ongoing quest to build intelligent systems. Please stay tuned for the continuation of our journey. If you enjoy the content, we kindly request you to like, subscribe, and share.